Have you ever wondered if breakfast really is the most important meal of the day? You probably have heard this phrase over and over for your entire life. But why is it the most important meal? And what happens if we just, skip it? Well, breakfast is an extremely important meal because it gives you the energy you need to start the day. You literally are breaking the overnight fast. And eating breakfast has also shown to contribute many health benefits such as weight control, improved physical and cognitive performance, and improved metabolic biomarkers. But is breakfast really the most important meal of the day? Let's face it, chances are that you know someone who seems to be very healthy but doesn't really take the time to eat breakfast. Well, it turns out that researchers can't agree either. And several observational studies have reported that people who skip breakfast tend to weigh more overall. And this observation may go against the common thought. For example, if you want to lose weight, eating 2 meals instead of eating 3 meals means you're eating fewer calories, doesn't it? Well, not necessarily. One theory is that breakfast skippers tend to get hungrier faster and therefore eat more calories later on throughout the day than regular breakfast eaters. The theory goes like this. Skipping breakfast results in spending the rest of your day making up those missed calories at the end, resulting in overcompensating and eventually leading to excess unwanted weight gain. However, most of these reports have come strictly from observational studies with little data from an experimental cause and effect setting. This means that many other factors could contribute to the weight gain aside from just not eating breakfast. So, in contrast to the common belief that skipping breakfast always leads to weight gain, randomized controlled research trials have actually shown that these common theories and myths about breakfast are hard to confirm. For example, when 2 groups of overweight and obese individuals were randomly assigned to either breakfast or to refrain from breakfast, there was no effect on the amount of weight lost in each of the groups. Another randomly controlled trial with lean individuals showed that skipping breakfast did not cause weight gain, nor did it lead to changes in resting metabolic rate or the number of calories that subject burned at rest that are required to sustain your basic physiological functions. Also, the overall daily caloric intake was the same whether the lean subjects ate breakfast or not. And this means that in this study, skipping breakfast did not lead to eating more over the next few meals. Now, one interesting difference, though, was that both afternoon and evening blood glucose levels were more stable in the group who ate breakfast as compared to those who fasted until noon. And stable blood glucose is usually a great sign for good metabolic functioning. In fact, if blood sugar is consistently high, this can lead to a host of other issues, including insulin resistance and even diabetes. Long story short is that there is no clear-cut answer in the research saying that breakfast is the key to gaining or losing weight or improving body composition. And oftentimes I'm asked, should I eat breakfast? And my answer is, well, do you like breakfast? I do this because what I've seen is that the key to making lasting improvements in body composition comes from working small exercise and nutrition habits into someone's lifestyle, rather than flipping their lives upside down from the start. And one main point to consider is that on the outside, if you eat breakfast or skip it, or you eat often or just once a day, every bit of food you eat has a dramatic impact on your body composition and your health and how you feel. So let's talk about what exactly happens to the food that you eat. How does it enter your body for storage as glycogen or stored carbohydrate, as fat or as protein? Well, many processes must happen inside your body to prepare the food you use for storage or to be burned as energy. Now, before the food you eat can be used as energy, it needs to be broken down further inside the body into the individual nutrients. And this process is called digestion. And then following digestion, the body must take up or absorb the individual nutrients to either use them or store them for later. This is called absorption. The bulk of this lecture will focus on the details of digestion and absorption, and we'll touch on how the aging process can interfere with normal digestion and absorption, and how that can affect body composition overall. We'll also talk about nutrient partitioning, which is how we use foods and how we can partition them into storage as fat or into storage as muscle based on our physical condition. Now, foods and beverages provide your body with nutrients that it needs to sustain itself. Now, that's pretty common. Now, the nutrients from our body, though, are split into two main categories. We have macronutrients and we have micronutrients. The macronutrients consist of carbohydrates, fats, and proteins, and these are used by your body cells to create energy. But the micronutrients, including vitamins, minerals, and water, do not provide calories or energy, but they are required for many physiological processes in the body, including digestion and absorption. You'll hear much more about the macronutrients and the micronutrients later in this course. But for now, to fully understand the digestion and absorption process, we will start with a brief overview to trace the food from the time it enters your mouth all the way through when it exits as waste. Once you take a bite of food, the first section of the gastrointestinal tract, or the GI tract, that it hits is the mouth. And obviously, the food then travels down the esophagus and enters into the stomach to be chemically and mechanically broken down into smaller fragments. And then after the stomach, these food fragments enter the small intestine, followed by the large intestine. And then whatever nutrients and materials the body does not use up along that process, they are excreted through the rectum and the anal canal. Now, along the route, your pancreas, gallbladder, and liver all help to digest and absorb the food by producing various enzymes. And these are specialty proteins that help reactions occur in your body. And the enzyme solutions they make also help with the breakdown and transport of foods. So, that's the brief overview. Keep these major organs in mind as we dive now into some more detail. Almost all nutrients within the food you eat must be digested before they are absorbed. And various physical and chemical activities from the mouth, the stomach, the pancreas, and the small intestine are responsible for digestion. And once you take a bite of your food, your teeth and your jaw muscles take care of the chewing of the food and mixing it with saliva to make the food easier to swallow. The water in your saliva, along with two major digestive enzymes called alpha amylase and lingual lipase, begin to dissolve and chemically digest your food. Yes, technically, digestion begins in your mouth. And once the food is mixed with saliva, we now refer to it as a bolus. The bolus leaves your mouth and travels through the pharynx and into your esophagus. The esophagus has a sphincter at the top called the esophageal sphincter. And this separates the oral cavity from your pharynx. Then a wave-like neuromuscular movement known as peristalsis occurs progressively to move the bolus of food down your esophagus. And then another sphincter called the gastroesophageal sphincter separates the esophagus from the stomach. And this is where your food is headed next. So this entire esophageal process usually takes about 10 seconds until the bolus of food has moved from the top to the bottom of your esophagus and then enters into your stomach. The stomach is the major site of chemical digestion, where any larger food items are broken down into individual nutrients. For example, large carbohydrates are broken into individual sugars, and large proteins are broken down into individual amino acids. This has to occur because whole carbohydrates, fats, and whole proteins are just too big to enter your body from your GI tract. So it is the smaller building blocks of the larger macronutrients that are needed to actually enter your body from the GI tract. So while the mouth and the stomach are referred to as digestive organs, they do things a bit differently. The mouth mainly takes care of the physical breakdown of food through chewing, and the stomach takes care of the chemical breakdown of food using very specific enzymes. The first enzyme is called pepsin, and pepsin breaks down large proteins into smaller amino acids. The second enzyme is called alpha amylase, and this enzyme may sound familiar to you as it already came into play when our food was still in our mouth. Alpha amylase breaks starches into simple carbohydrates, but not for long because the acidic environment of our stomach actually stops the majority of the alpha amylase activity. Now, the third enzyme to take note of in the stomach is called gastric lipase. This enzyme breaks down some fats into smaller components that are easy to absorb. Along with these three main enzymes, several other hormones and secretions play a role in the chemical digestion activities of the stomach. So the stomach is where partially digested food is mixed with stomach juices and enzymes to create a substance called chyme. And once food is fully mixed and the chyme is ready to be emptied out of the stomach, it moves through yet another sphincter called the pyloric sphincter and enters into your small intestine. Now, the small intestine is your main site for finishing up the digestion process. It is also the main site that absorbs all of the nutrients that you've just broken down. And although its name says small intestine, this organ is far from small in both length and in importance. For example, if you were to unravel the small intestine into a straight line, it would stretch out to be about 20 feet long. Also, the surface area spreads out to be about 300 meters squared. So picture a 3-foot wide walkway that is more than 3 football fields in length. This is the amount of space that your small intestines would take up. Now, this is a huge surface area, and it's a unique aspect of the small intestine as it allows us to maximize digestion and absorption. The reason the small intestine has such a large surface area is due to circular folds known as the folds of Kerckring. Now, these folds have many finger-like projections called villi that project off of these folds and into the lumen, or the inner side of the small intestine. And hundreds of these intestinal cells line the villi in order to absorb and transport the nutrients. These cells are called enterocytes. And these microscopic structures, called microvilli, are tiny, hair-like projections that make up the villi themselves. Now, these small microvilli make up an important section of the small intestine, known as the brush border. It is within the brush border where all of the intestinal digestive enzymes are produced and stored. Almost all of the digestive activity in the small intestine occurs in the brush border. Now, once all the nutrients are broken down into their simplest forms, they are then taken up into the cells of the GI tract to be transported throughout the entire body. This process is known as absorption. Most of the carbohydrates, fats, and proteins that you consume are generally absorbed within about 30 minutes after reaching the small intestines. Any material that is not absorbed by the time it reaches the end of the ileum, or the last portion of the small intestine, passes through something called the ileocecal valve, and then into the large intestine, or the colon. The large intestine is about 5 feet long, and all of the remaining food items or intestinal material that enters the colon is still in a liquid form. But by the time it reaches the end of the colon, also called the sigmoid colon, the material is solid or semi-solid. This is because the large intestine is the main site for water reabsorption and for the reabsorption of electrolytes. Overall, it can take anywhere from 12 to 70 hours for the food remnants to pass all the way through the colon, and waste products are eventually excreted as fecal matter through the anal canal. Now, your body composition overall is highly influenced by the digestion and absorption of the nutrients from the food you eat. So what's next? After the nutrients are taken up into the small intestine cells, where do they go? Do they just hang out there, or do they move somewhere else? Well, there are actually several answers to this question, several extremely detailed answers. Let's begin with carbohydrates. Through digestion, more complex carbohydrates are eventually broken down into individual units known as monosaccharides. The 3 monosaccharides are glucose, galactose, and fructose, with the most common being glucose. Now, as we talked about earlier, most nutrients are absorbed somewhere along the length of the small intestine, through the brush border and into the intestinal cells. And carbohydrates are absorbed very efficiently and are usually cleared of the small intestine more quickly than fats or proteins. Remember I mentioned earlier that carbs make less demand on the body's metabolism than proteins. Well, glucose is absorbed in the small intestinal cells by a protein complex called the sodium glucose transporter. This is an active process, meaning that energy, or adenosine triphosphate, ATP, is required to make this happen. And after the glucose is absorbed into the intestinal cells, it is then transported out of the cell and into the bloodstream. Now, some of the glucose simply diffuses into the blood, but a carrier protein called GLUT2 transports much of the glucose from the intestinal cell into the blood. Now, once glucose enters the blood, it goes directly to your liver. This is called portal circulation. The liver is the main site of glucose metabolism, so it gets first choice on what to do with the incoming glucose. It can use it, store it, or simply let it move on. And any glucose that is not metabolized or used by the liver passes through to systemic or whole body circulation. From here, glucose travels to various other tissues where it can be taken up through a facilitated transport process using other transport proteins before it is used within that tissue. Next, we have fat. Now, digestion of fat begins in the mouth by the action of the enzyme called lingual lipase, and only very small amounts are broken down in the stomach. The bulk of triglyceride, or fat, digestion occurs in the small intestine. So before fats are broken into their component parts, they first must be emulsified by bile. Well, bile is produced in your liver, but stored in your gallbladder. And essentially, fats have to enter the aqueous environment of the small intestine. But fats are hydrophobic or water-fearing, so emulsification by bile helps fat break apart into smaller lipid droplets that can exist in the small intestine before being broken down. You may have heard of emulsification if you've tried to mix an oil and a vinegar salad dressing. They always separate. But if you add an emulsifier, you can get them to mix and play nice together. It's that bile that allows fat to play nice in the small intestine. So once fat is present in the small intestine, a hormone called cholecystokinin, or CCK, is secreted. And then bile is released through the bile ducts into the small intestine, and the emulsification process begins. And once emulsified, the pancreatic lipase acts on the fats and further breaks them into smaller units that can be absorbed and transported for use. Now, unlike carbohydrates, fats are a little tricky when it comes to their absorption and transportation. They are naturally insoluble in water, and because of this, they cannot move through the brush border into the blood as an individual lipid unit. So to solve this problem, broken down fat particles mix with bile salts and form a water-soluble substance called a micelle. This micelle then interacts at the brush border of the small intestine, and fat particles move out of the micelle and into the intestinal cell, and the water-soluble bile salts continue down through the small intestine until they are reabsorbed and sent back to your liver. So, after the broken down fat particles, which includes free fatty acids, monoglycerides, and some cholesterol, and phospholipid particles in the intestinal cell or enterocyte, they actually reform or combine back together into a larger original triglyceride form. Now, you might ask, what's the point of breaking the fats down just to have them put back together again? Kind of sounded pointless, doesn't it? Well, the only way that fats can be absorbed out of the small intestine is in their smallest, most broken down form. But now they need to be transported. Well, as we noted earlier, fats are not only broken down differently than carbohydrates, they also travel differently. Fats must travel through the lymph system instead of the blood. The lymphatic system is a network of vessels that transports nutrients of the cells and collects cell waste products. The only way fats can travel out of the intestine and into the lymph is by combining into particles known as chylomicrons. Now, the reformed fats combine with fat-soluble vitamins like vitamin A, D, E, or vitamin K, and a protein layer to form the full chylomicron. The chylomicron serves as the carrier for all digested fats that come from the food you eat. And when these chylomicrons are formed, they leave the intestinal cell and move into the lymphatic system. In a slow process, these fats move out into the lymphatic vessels and eventually into your blood, where they freely travel to tissues to deliver fats for use or for storage. Some fat will be used by your muscle cells to produce energy, and some will be deposited into your fat cells. Now, there are many things that can affect how fats are used and stored, including when you last ate, your overall calorie intake for the day, your exercise habits, and how physically fit you are. I'll discuss this much more later in the course. Now, because this transportation process for fats is relatively slow and somewhat individualized, it could take anywhere from 30 minutes to 3 hours after you eat a high-fat meal for your blood lipids to reach the highest level. After about 5 to 6 hours from your meal, however, the chylomicrons will have delivered the fats to the designated tissues and your blood levels should return back to normal. Now, our last macronutrient to discuss is protein. The structure of protein is very complex. Remember, we talked about the digestion of protein making more demands on your body's metabolism. Well, that's because of the complexity of protein. Proteins stay fully intact until they get into your stomach. And large proteins are broken down into individual amino acids in the stomach by the very acidic stomach juice. And proteins that are still intact after leaving the stomach are broken down further in the top portion of the small intestine. The end products of protein digestion are free amino acids, which are absorbed into your intestinal cells. Now, proteins are absorbed in a process more similar to carbohydrates than that of fats. And this process occurs along the entire length of the small intestine. Amino acids, just like glucose, require sodium-dependent carriers to get them into your intestinal cells. And there are several uses for particular amino acids within the intestinal cell. However, amino acids that are not used within the intestinal cells themselves are transported out of those cells and into the blood and make their first stop at your liver. About 50 to 65% of all of the ingested amino acids are metabolized in your liver. The rest of the amino acids are used in other tissues, particularly the skeletal muscles, your kidneys, and the brain. In fact, these amino acids are used by skeletal muscle, for example, to directly repair muscle or maintain muscle mass or even help with growth of muscle, and especially if it's combined with the proper exercise routine. It is the skeletal muscle mass that has a huge influence on your muscle mass and your body fat ratio. And the entire process of digestion and absorption is important to understand because it can determine how the food you eat makes you feel, and the food you eat is ultimately stored as body fat or glycogen or used as energy. Now that we have discussed macronutrients, digestion, absorption, and transportation in detail, I want to touch briefly on the micronutrients. So while it's the macronutrients' job to provide the body with energy, micronutrients, on the other hand, do not provide direct energy. However, they are vital in order to make all of the digestive processes occur, along with hundreds of other reactions and processes within the body. So the micronutrients are involved with energy production, but they just do not directly provide energy. The water-soluble vitamins, vitamin C and the B-complex vitamins, are absorbed and transported through the blood. With the exception of vitamin B12, which can be stored in your body for several years, water-soluble vitamins are not stored in your body for long periods of time. They are either used very quickly in the body or excreted in the urine. So we need to get them from the food we eat. Fat-soluble vitamins, which are vitamins A, D, E, and K, are absorbed and transported very similarly to fats. They need to be packaged into the micelles to be absorbed and transported by chylomicrons throughout the lymph. Now, unlike water-soluble vitamins, excess fat-soluble vitamins can be stored in the body for a decent amount of time. And for this reason, fat-soluble vitamin deficiencies are much less common than water-soluble vitamin deficiencies. So back to the question about breakfast. As you can now understand, quite a bit happens inside your body after you take that first bite of your breakfast. For the most part, the GI tract of a healthy individual works like a well-oiled machine. Along with the digestive system itself, the endocrine and the nervous system play a major role in regulating digestion, absorption, and transportation of the nutrients. And the GI tract is really amazing. I mean, unfortunately, as people start to age, some functions of these systems begin to slow down. And the main cause for these changes is that the degeneration of something called the enteric nervous system. And this is the nervous system specifically for the GI tract. The enteric nervous system controls muscle contractions in the esophagus and the stomach and the colon. And when it degenerates, the movements of food and food-like products through the GI tract usually slows down. And this can lead to serious GI complications, including dysphagia, which is a swallowing difficulty, GI reflux, and even constipation. And gastric acid secretions can also be minimized with age, leading to bacterial overgrowth and inflammation. So, along with biological and nervous system complications, elderly individuals may experience what has come to be known as anorexia of aging. No, this doesn't mean the elderly person has developed a psychological eating disorder. Anorexia of aging is referring to a physiological, age-related reduction in appetite and energy intake, which ultimately leads to significant amounts of weight loss and muscle wasting. Basically, as you age, there may come a time when you just don't feel hungry very often. While this may lead to weight loss, this is not a good thing. Oftentimes, massive amounts of muscle mass is lost too. And ultimately, low muscle mass prevents mobility. Well, your best way to avoid or slow this age-related reduction in appetite is to simply make sure you are leading a healthy lifestyle. Sounds pretty easy. But do some basic things like see your doctor regularly, exercise, and nourish yourself with foods that contribute to your health. I want to touch on one final topic of interest that you may have heard about. This is called nutrient partitioning. And the term is used to describe how the food you eat is stored or partitioned into a specific area like muscle or fat. So the question is this: can I eat a particular way to digest and absorb foods for the specific purpose of improving body composition? At the most basic level, the more of one type of food you eat, say predominantly carbohydrate, the more of that fuel you will burn for energy. And the same thing would go for fat. The more of it you eat, the more of it you will use. What you really need to know is this: exercise is the most important and powerful tool to help you use your foods that you eat to improve your body composition. If you're active, you will tend to use the foods you eat to power your exercise. But if you are sedentary, your body will tend to partition the foods you eat to being stored as fat. So no matter if your diet is mostly carbohydrates, fats, or proteins, if you're sedentary, only so much of your food will be used and stored for a healthy purpose before getting stored simply as body fat. In fact, recently, Dr. Edward Archer from the Nutrition Obesity Research Center at the University of Alabama at Birmingham produced a short video on this specific topic and explained further how exercise is what drives the nutrients we eat towards a useful end rather than being stored simply as excess body fat. You see, if you don't exercise, you're essentially always have a full gas tank. You never really tap into those fuels to create any sort of deficit. So when you eat, no matter if it's a small meal or a large meal, there's less of an opportunity for your body to actually use the incoming fuels. And as a result, you'll probably store them as body fat. But when you exercise, like lifting weights or walking or working out vigorously to any extent, your body has the best chance to use the food you eat in a positive way. Some people use nutrient partitioning strategies to try and fuel the body at the most optimal times to avoid excess weight and excess fat gain. Well, this is still a bit controversial, but we'll talk more about it later. For now, Just know that exercise is the key to creating an internal environment in your body where the digestion and absorption of the foods you eat is optimal for powering your muscles, avoiding excessive fat storage, and ultimately improving your body composition. So back to breakfast. Is breakfast really the most important meal of the day? Well, that's for you to find out. Over time, your body will let you know what it needs. If it needs you to eat breakfast, it will tell you. If you listen to your body, it will respond in a positive way. You will feel healthy and ready to take on the day. If you don't listen to your body and don't provide the nutrients it needs at the right time, it will also respond. For example, if you're like me, then you probably have overeaten on occasion and then feel sluggish and tired. We get great clues about the food's needs we have and our overall health all the time. We just need to know what to listen for. All of this occurs because essentially you are what you eat. Really, and my hope is that having a better understanding of the digestion and absorption process will help you to tune in more effectively to what your body is telling you. Our body's cells, which make up who we are formed and nourished by the foods we eat. This is what we'll talk about next. So try this. Pay attention to the foods you eat and how they actually make you feel and perform. That's my plan. It's time for a snack.